Alright guys, so in this video we're going to be talking about how we can go use our limits to find the slope of a function. So at the slope of a function at any given point. So back in algebra, if we wanted to find the slope of a line, we would take 2 points, which in our case will be x2, y2, and down here we have x1. Whoa. We got x1, y1. Okay, and then we would use this formula where m equals the change in y over the change in x. And we could calculate our slope from there. Now, what happens if we want to find the slope of a nonlinear function? Suppose we have a parabola and we want to find the slope at this point. Well, one thing we could do is we could take some points on either side. We'll call them x. We'll call them x2, y2, and x1, y1, and we can use this same formula to kind of approximate what the slope will be. So it's not going to be perfect, but we can end up with what's called a secant line, which is approximating what this other slope is going to be at the tangent at this particular point on the graph. Now it's going to approximate it, but we can make it work. So let's call this function y equals x squared. Okay, now let's make a table of values, and we'll try to approximate the slope of the function at that point. So we got some x's and we got some y's. We'll do 1, 2, and 3, and what we're going to be doing is we're going to look for the slope of the function at x equals 2. Okay, so we have 1, 4, and 9 over here on this side. Okay, so let's pick these two sets. Pick this set and this point, these 2 points, and we'll use those in our formula for our slope. So we'll call it m secant. And it's going to be equal to y2, which is 9, minus y1, which is 1, divided by x2 minus x1. Okay, and that will give us 8 up here and 2 down here, which will give us 4. And that is the approximate slope at this point, which is x equals 2. Okay. Now, this is going to give us an approximate answer, and it's not going to be perfect. If we wanted, it's probably fine. It might be fine in this case, but suppose we wanted to get more accurate, we could pick points that are closer and closer and closer to x equals 2. And if you were doing it using a computer, that would be great. I'm just too lazy to do that, so I'm going to use our tools that we learned about in the last video, which are limits, and we're going to establish what's called the limit definition of a derivative, where the derivative is the slope of the function at any given point, in our case x equals 2. So the definition, well, we'll just call it m for now, we'll call it m tan, is equal to the limit, as h is approaching 0, of our function of x plus h minus f of x divided by x plus h minus x. Alright, so this is going to be our limit definition of the derivative, and we're going to use this to find the exact value of the slope of the tangent line at the value of x equals 2. And you can use this no matter what function it is. You can use this definition of the derivative and plug in your values this way. This is kind of like using that secant line, except we're saying as you get closer and closer and closer to x, as you pick values closer and closer to that value, you're going to get closer and closer to what the actual value is of the slope at that point. And that's what this this limit definition is giving for us. So that's what it's doing for us. So let's go ahead and use that. So we have mtan is equal to the limit as h is approaching 0 of our function of f of x plus h, where our function was y equals x squared, right? So, and x equals 2, so we have 2 plus h squared. Okay, minus 2 squared divided by, and we can see that the x's cancel here, so it's just divided by h. And we could simplify this formula for you, but I just wanted you to see that the resemblance between the limit definition and the original definition of our secant slope. Now, let's go back to this. We have the limit, and if you need extra practice working out some limits so you can get some experience, you can always go on to OpenStax Calculus 1. They have a free book online, and you can go to the homework problems from Chapter 2, and they have a whole bunch of homework problems you can work out, where you can work out limits of various functions and get some practice in. So we have the limit as h is approaching 0 of this, which is going to be 4 plus 4h plus h squared minus 4, and those cancel out, divided by h. Now we can factor out an h out of the top here, and we'll get the limit as h is approaching 0 of h times 4 plus h divided by h, and we can see that those cancel out, and then our second h is going to go off to 0 as we approach 0. So the answer to this is mtan equals 4. Now you can see that this is actually the exact same as our secant line, and we just got lucky in this case. But I wanted to show you how you could approximate it using the secant line, but the actual value of the derivative is also 4 in this case. I should have chosen a different example, but we'll go ahead and stick with this. But you can use this limit definition of the derivative for any function that exists and get the right answer. So in the next video, we'll talk about using this on various functions, with like trigonometric and exponential functions, and we'll get into how to find different derivatives from there. So I'll see you guys in the next video.